Then you've considered the vehicle architecture. You've thought about what are the wetted surfaces, which regions I need to model, ducts, brake ducts, everywhere the flow is going. You looked at the tire contact patches, all of that. Then you start thinking about setting up a CFD simulation. You need to think about your domain, which is where the car sits, where you specify some boundary conditions, an inlet and outlet, a moving ground, and things like that. Uh, there are some thumb rules for these things, and we'll understand a bit more in detail tomorrow why those we have those. For example, the size of the domain. You need your boundary conditions, the inlet and outlet, to be far enough so that they don't influence your car, um, and the roof as well, for example. And then you've got yeah, you've got the boundary condition of the ground. It'll be a moving ground, or if it's a slip. It depends on what you're trying to do. If you're trying to simulate road conditions or track conditions, or you're trying to simulate a specific wind tunnel condition, you might have a wind tunnel condition where you've got small belts, moving belts, and you might want to replicate that. So this road setup will depend on what you're trying to do with the safety simulation. So you have to think about that in the domain, as such. Hopefully, I'm not going too fast. But we can come back to this within the question answer session if you have any questions about this. Then the next step for me in this sort of thought process is you have to place, because you're already thinking about creating the domain, and you need to be thinking about the contact patch and all that. All of that is tied into the attitude of the car as well. So the ride height at which the car is sitting, and that is complex because that's completely dependent on what you're trying to simulate. And for an F1 car, for a race car, you want to simulate a lot of different conditions, because the most important things are cornering conditions for a race car. That's where you want your aero forces to be at its best. Um, and different speeds of corners have different car attitudes. The car is at a different ride height, a different roll, different steering, a wide variety of steering angles, for example, different corner speeds. So it's a huge range of attitudes and positions of the car that you can simulate. Um, the race car that we're considering this workshop, they're all mostly open wheel. There's no body work around it. So how do you define ride height? It's a bit different because in the automotive industry, in my daily work now, the ride height definition is quite different. We On a road car, we define it relative to the wheel arch, which sits around the wheel. But for a race car, there's no bodywork near the wheel most of the time. Even if there is, it's like a little winglet or something. So how do you define ride height? It's slightly different. What you do is you define a reference plane on the car at the bottom of the floor. Usually, it's where the skid plate is. So you have a Z-aligned reference plane, just as a starting point, and that's your reference. And the distance from this reference plane to uh, the ground plane at the front axle and the rear axle is your front and rear ride height. So if you imagine a reference plane that touches the car and will move as the car moves, as the car pitches, rolls, and all that, then from that plane to the ground will be your front ride height measured at this front axle. And from that plane to your ground plane measured at the rear axle is your rear ride height. So that's how uh, most uh, most groups define front and rear ride height for a race car. And that's one of the key aspects to be thinking about when you're setting up the car in your domain, in the CFD domain. Then the next thing would be, and this we talked about this briefly. Uh, Again, very connected to everything that we've been discussing, the contact patch, all of that. It's where does the whole wheel and suspension sit? it depends on what car attitude you're trying to simulate. So, for example, if you're trying to do a braking condition and you've got complete front pitch, your front suspension will be in a different position to rear suspension. Um, in the past, a lot of CFD was done maybe at a single ride height, a few different yaw angles and things like that. But now, uh, the aerodynamic behavior at the other ride heights is it's critical, and because we have the resources, we also do it in CFD. So it's quite easy to do it in the wind tunnel because the wind tunnel model is designed to do that. You've got extreme level of motion control in the wind tunnel, so you can test at whatever car attitude you want, uh, in a high speed corner, low speed corner, medium speed, braking, straight line, whatever condition you want. You can put that model in that condition in a wind tunnel. Uh, but CFD is obviously a bit more difficult. It'll take more time, because each of those attitudes is a simulation in itself. So it's not as easy to acquire data from a CFD simulation. So you tend to focus on some points of a corner, for example, the apex or entry exit conditions, and depending on what a particular group wants to look at, maybe the front wing group, it depends on that what your right eye, your roll, steer, all of that setting is. There is an advantage of running these kind of simulations in CFD. They, it's being leveraged quite heavily now. The advantage is that when you go to these kind of extreme conditions, it's difficult to understand just from a pure experiment in the wind tunnel what might be happening, the mechanisms that might be happening, and CFD can really help in that. And the way that we leverage this capability is using morphing tools that allow the mesh to be modified in a very easy way. So you can define a suspension geometry, a kinematic model, or even just a stick model of your suspension parts, your wheel attached to it in a starting camber toe and everything, and a lot of teams, a lot of CFD groups have a pretty complex model that will position the wheel exactly to the simulation that you want, in the sense that if you want a high speed corner apex, it will put the wheel in the position that the wheel would be in that condition on the racetrack. And that's key because once you have the wheel positioned correctly, then you can then define the contact patch. And the aerodynamic load acting on the tire comes into this as well when you define the contact patch. So from this side, the key takeaway is that you've got a lot of morphing tools that a CFD group will then automate completely, as and when you choose a particular condition, it will set up your suspension and wheel geometry and tire geometry to that condition.